Hello everyone. This video is for section 22.3. In this section, we will give several examples of determining big O notation for repetition, sequence, and selection. Let's look at this repetition. This is a simple for loop. For I is from 1 all the way to n. For each I, we're going to perform this addition. So what is the time complexity? This statement, addition, assignment, it is a constant time. This is executed n times. So the total time is a constant time times n. The constant multiplicative can be removed. So the result is O of n. This is the linear time. If you double the input size n, the time is doubled. Let's look at this performance test. When you actually run the program, you can see the time complexity is in the linear growth. So for this is the test. We have this is the loop right here, the for loop. I from 1 to n. For each I, we're going to perform this statement. We get a time before the loop and the time after the loop. And now we're going to display the difference between the two time. For each of this test, we put this in a method, get time. So for the time is 1 million, 10 million, 100 million, and so on. And you can see the difference now here. For the 1 million, it's very fast. It's 0 milliseconds. And the 10 million is 16. 100 million is 63. Now you see the next, if you increase the input 10 times, and the time is roughly 10 times more. And see this right here, increase the time 10 times, and the time is 10 times more. So the theoretical notation, the big O, predicts the actual execution time. Let's look at this nested loops. Inside this for loop, and we have another for loop. So here is I is 1 and all the way to n. Now for this j is 1 and to n. So this is inside, this is n times. For every I, this is executed n times. So now the time is, and this statement is the constant time, and this is inner loop executed n times, the outer loop executed n times. The total complexity is this, is a constant time times n and times n. Ignore multiplicative constant c, and the time is order of n squared. Let's look at this one here. It's slightly different from the previous one. So here is, look at the j is 1 to all the way to I, depending on this I. So let's look at the time here. This is a constant time for this statement. And this inner loop executed I times. And now this is the I is 1 to n. Look at the total time. You can write this one here. So if I is 1, so this is 1 time. If I is 2, so this is 2 time. This is the constant c. And if I is 3, just 3, and 4, and all the way here. The last one is I is n, so this is n times c. Add all this together, summation, and you can see this is what we have. Now, this is the n square, and this is n. This one is non-dominating part can be ignored. So we focus on the dominating part is n squared. And for this is c over 2 is a constant factor. It can be removed. So now finally it's reduced to order n squared. So the time complexity of this loop is actually the same as the previous loop when n is very, very, very large. All right, let's look at this here. Now, I have this is 20. This is the constant time, and here it is 20 times, executed 20 times. It's still the constant time is 20. So this time is 20 times c and times n. That is order n. It's a linear time. So the complexity is dependent on this n. When this n grows and the time grows. And this is fixed. So we're looking at the growth rate. So it doesn't matter how big is 20, maybe even 22 million, it's still a constant number. And n is the one we're looking at. N is going to be very, very large. Look at the sequence here. There's 2 parts in this program. This is for loop. It's fixed. Here's 10. And this constant 10c. And this one here, this inside is 20. So this is the n. Now look, the overall time, it is this. It's from this first part is 10 times c. And this, the second part is 20 times c times n. So the overall is a linear time. It's order of n. Look at the selection here. This test list data contains E to check if E is in the list. This is text order of n time. And now this is a constant time. And if this condition is false and coming here is this time is a loop for each loop for every element in the list and print it. So the time is order of n time to execute this for loop. So the overall time, it is linear time. You add all this together, and this is the test time, and plus the worst case of if else. So if this is the case else, and that is order of n time. In the best case, it's going to be 1 time, but we're now looking at the time complexity. We consider the worst case. Finally, let's look at this example here. We're going to compute A's n, so the power A, the power raised to n. And this is the loop we're going to write. Just have this result is 1, and we're going to do multiply A to the result n times. So the complexity is order of n. Now we compute the same result and assume, without loss of generality, we're going to assume that n is 2k. Now we're going to use this clever approach with this result initialized as A. So we're going to time result times result, result times result. We only need to do this k times. We will get this. And the complexity, it's order of n times this is, it should be order of, this one should be order of k. And so what is k? It's k is log n. And the best for this log is 2. So this is the complexity. Let's review the time complexity for this examples here. Constant time. The big O notation estimates the execution time of an algorithm in relation to the input size. If the time is not related to the input size, the algorithm is said to take constant time with the notation order 1. For example, a method that retrieves an element at a given index in an array takes constant time because it does not grow as the size of the array increases. Doesn't matter how big the array is. If you want to get an element from the array using the index, that is the constant time. A logarithmic time, an algorithm with order of log n time complexity is called a logarithmic algorithm, and it exhibits a logarithmic growth rate. The base of the log is 2, but the base does not affect a logarithmic growth rate. So it can be omitted. In algorithm analysis, the base is usually 2. Linear time. An algorithm with the order of n time complexity is called a linear time algorithm, and it exhibits a linear growth rate. So when the input doubles and the time doubles. Quadratic time. An algorithm with the order of n squared time complexity is called a quadratic time algorithm, and it exhibits a quadratic time growth. If the input is doubled, the time is quadrupled. That's all for this section. See you on the next section.